Have you ever stopped to think about how your computer is doing so many things at once and somehow not just completely falling apart? I mean, you're editing a document, you've got music playing, notifications are popping up, it all feels seamless. But that multitasking magic, it's not an accident. It's all managed by a set of invisible rules for something called inter-process communication. This is the secret language that lets all your apps play nicely together.
So let's kick this off with a really simple question. How can you and a coworker both be in a shared document at the same time, making changes, without turning it into a garbled mess? Or how can your computer update a system file while another program is trying to read it? You can imagine, if there were no rules, the result would be total chaos and corrupted data. And that right there is the core problem that inter-process communication exists to solve.
All right, to get to the answer, we first need to get one thing straight. In the world of your computer's operating system, programs, or as we call them, processes, are all lone wolves. Some of them absolutely have to cooperate to get anything done.
And they basically fall into two camps. On one hand, you have the independent process. Think of this like a novelist locked away in a quiet cabin. Nothing they do affects anyone else, and no one else's work affects them. But then you have a cooperating process. This is more like a team in a busy newsroom. They're all sharing resources, they're talking to each other, and their work directly impacts what everyone else is doing. And that little phrase there, shares data, that's the key to everything.
So why do we even bother with this complexity? I mean, wouldn't it be simpler if every process was independent? Well, yeah, but the benefits of cooperating are just too good to pass up. Information sharing is obvious. It lets us work on the same file. Computation speed up, that's like hiring a bunch of chefs to work in the same kitchen. You get the meal ready way faster by splitting the work across different processors. Modularity means you can build a massive, complex app piece by piece, like an assembly line. And convenience? Well, that's you, right now. Maybe listening to music while your code compiles and a document prints in the background.
Okay, so we know why they need to cooperate, but how do they actually, do it? How do these separate programs talk to each other without just shouting over one another?
It really boils down to two fundamental ways. First, you've got shared memory. Think of this like a public whiteboard in an office. Any process that has permission can walk up, read what's on the board, erase something, or add something new. It's super fast. But as we're about to see, it can also be super dangerous. The other method is message passing. This is more like passing notes in class. It's way more structured and safer because you have to explicitly send a message and wait to receive one. It's a bit slower, but a lot less chaotic.
So let's really dig into how that shared whiteboard, that shared memory model, can lead to absolute disaster if you don't have some very strict rules. And for that, we're going to use a classic example, the bank account problem.
All right, here's the setup. We have one shared bank account, and it's got 50,000 rupees in it. Now, two things are about to happen almost the exact same time. One process wants to deposit 10,000 and another process wants to withdraw 5,000. So the final balance should be 55,000, right? Seems simple enough. Let's see what actually happens.
First, the deposit process gets its turn. It reads the shared balance, that's 50,000, and copies it into its own private little workspace. Let's call that workspace A. Then it adds the 10,000 deposit. So now, in its private space, A is equal to 60,000. But, and this is the critical part, it hasn't actually updated the official shared balance yet. And bam! Before the deposit process can save its work, the operating system interrupts it and gives the withdrawal process a turn. So what does it do? It also reads the shared balance. And what balance does it see? It still sees the original 50,000. It has no idea what the deposit process was just doing. So it subtracts its 5,000 and calculates its own private result of 45,000.
The withdrawal process is quick. It finishes its calculation and writes its result, 45,000, back to the official shared bank account balance. From its perspective, the job is done and everything is correct.
But then, the operating system switches back and lets the deposit process finish its turn. Remember, it's been holding on to its private calculation of $60,000 this whole time. Completely unaware of what just happened, it saves its result to the shared balance, overwriting the 45,000 that the other process just wrote.
In the final result, our bank account has 60,000 rupees. The 5,000 rupee withdrawal, poof, it's just vanished into thin air. It's gone. All because the two processes raced to update that shared value, and the last one to write its result won the race, erasing the other's work.
This kind of disaster has a very specific name. It's called a race condition, and it's one of the most fundamental and frustrating challenges in programming.
It means the outcome of your software depends on the totally unpredictable timing of which process happens to finish its work last. It's a recipe for chaos.
So that was the problem. That was the chaos. How do we bring order to it? Well, we need to establish some really firm rules for how these processes are allowed to access that shared whiteboard. The very first step is to identify the danger zone, that specific little chunk of code where a process is reading, changing, and writing the shared data. We call that the critical section. You can think of it like a room that can only hold one person at a time. Our goal is to basically build a really secure door with a lock for that room. And any good solution, any good lock for that door, has to meet these three conditions. They're non-negotiable. First, mutual exclusion. That's just a fancy way of saying one at a time, period. Second, progress. This means if the room is empty and someone is waiting to get in, you have to let them in. You can't just keep the door locked for no reason. And third, bounded waiting. This ensures fairness. You can't let a process wait forever while other new processes keep cutting in line. Eventually, everyone has to get their turn.
So, how do operating systems actually enforce these rules? How do they build that lock and key system? Well, one of the most classic and powerful tools in the toolbox is something called a semaphore. The best way to think of it is as a traffic cop for your data.
At its heart, a semaphore is really just a simple number, an integer, that acts as a gatekeeper. It's controlled by two special operations, wait and signal. And the key here is that these operations are atomic, which means they are guaranteed to happen all at once, without being interrupted halfway through. The best analogy is to think of a semaphore as the number of keys available for a room. Before a process can go into that critical section, it has to get a key. When it leaves, it has to return the key.
And they generally come in two flavors. A binary semaphore is the simplest type. Its value is either 0 or 1, so key available or key not available. It's like having a single key for a single room, which is exactly what we needed for our bank account problem. Then you have a counting semaphore. Its value can be any number, and it's used when you have a whole pool of identical resources, like an office with 5 printers. The semaphore starts at 5, and every time someone uses a printer, the count goes down by 1. So here's exactly how that key exchange works. When a process wants to enter its critical section, it calls the wait operation. This is it asking for a key. If the semaphore's value is greater than 0, great. It just subtracts 1, taking a key, and goes right in. But if the value is already 0, that means all the keys are in use, and the process has to stop and wait. Then, when it's done and leaves the critical section, it calls signal. This adds 1 back to the value, returning the key, which might just let another process that was waiting finally get its turn. Okay, so let's pull all of this together. After going through all that, what's the big picture? What's the major takeaway from this whole deep dive into how our computers really work?
Well, it's that these powerful tools are always a trade-off. Semaphores are amazing. They efficiently guarantee that one-at-a-time rule and prevent race conditions. But they are a very sharp tool. If a programmer isn't careful and makes a mistake, like they forget to call signal and return the key, they can create brand new, even worse problems. They could cause a deadlock, where two processes get stuck, each holding a key that the other one needs, and they just wait for each other forever, frozen. Or they could cause something called priority inversion, which is a nasty bug where a low-priority task holding a key can force a super important high-priority task to wait for it.
The thing is, this whole complex dance of cooperation, of managing shared stuff and preventing these race conditions, it's happening billions of times a second inside every device you own. It's this invisible, absolutely essential foundation that stops our amazing multitasking digital world from just collapsing into complete chaos. So the next time you're juggling a dozen apps, just take a second to appreciate all the silent traffic cops inside working hard to keep everything running smoothly.